here. I will also give a quick introduction about myself so that you understand a little bit more where I'm coming from and where my models are inspired from. But before, let's start with a brief, I guess, exercise just for fun, which might be only a little bit related to the presentation. Who of you used LaTeX? Who of you used a LaTeX Beamer? Who of you used TickSet? Okay. For those who know, all of these slides are made in TickSet. Enjoy. For those who don't know, each thing up here on the slide is programmed and not drawn in any programming. So it's all in LaTeX, TickSet programming language. Okay, with this, so besides spending a lot of time in LaTeX, I did my undergrad in Austria, and I'm actually a trained civil engineer. So I studied construction management followed by computational mechanics. So I have 2 masters. Then I went to ETH, where I looked into infrastructure management, where I fall in love with network science. And after my time at ETH, I joined the University of Zurich as a postdoc working with Professor Scholtes, and we'll show some of our work here in this presentation in the computer science department on higher order networks. Afterwards, I joined as an assistant professor at the School of University in Liverpool, followed by a brief stay in Cambridge. And then, I decided to come to the US and see how things are done on the other side of the ocean. Also had some, or still have, collaborations in Asian countries. Again, my research actually started with natural hazards. And so those are countries which are quite prone to natural hazards, so I have a strong relationship and work experience with them. Also about this a little bit later in that. So what I'm actually doing in Princeton, to give you a quick overview, so that's some topics I'm interested in, and hopefully some of you also might be interested in one or the other. So I'm working on systems of systems, network science, and certainly quantification. I will tell you a little bit more about the topics as long as we're going through the presentation. Also, I will give a quick shout out already at the beginning. So this is my current staff. I have 1 postdoc, 3 PhD students, which are in Princeton, and 2 co-supervised PhD students. And a lot of the work you will see is actually made by them and made possible together with them. So let's start with a quick motivation. What are complex infrastructure systems? So what I'm interested in. And here's already one very prominent infrastructure systems, which causes a lot of problems, but also makes our world running. We all use road networks in order to come here today. So one of the research we're interested in is understanding these kind of transportation networks. We also work on power grids, where we'll show you some insights as well. So that's also other networks we're interested in. So how power grids work, how they transform over time, how renewable energy will be integrated, what does it mean in terms of reliability, resilience, and then a lot of other questions arise there. We also have work on mobility. Again, having road networks, the physical network now already implies that someone is using them, and that the question is, do we do this in an efficient way? Can we improve them? What are the bottlenecks in here? Speaking about bottlenecks, we're also interested in subways. Again, also a network system used by millions of people. And there also we see severe problems, especially in terms of when there's flooding happening. So that's one study we're doing in New York, is like what happens when certain links are actually failing in these kind of systems. Another system, infrastructure system we're interested in is flight networks. Also there we have a project working on flight paths and how they're influenced by hurricanes, and what does it actually mean for airlines and for our air transport. Again, another motivational slide on things we're working on is transportation shipping networks, so how goods will be transported. Here we don't have an underlying network topology, but still a lot of moving parts which come together in some or the other way. And then the last part I'm interested in with my group is social networks, but here again we have Facebook network, but actually what we're working on historic social networks, so how music theory developed over space and time, again with the component of space and time. So there we have a new project, and I'm happy to talk about this as well a little bit. So that's the motivation. So that's things we're working on. Again, they're all very heavily engineered networks, maybe this one, but every other network is very heavily engineered. And they have two common things, what we're interested in.
They can't see your slide, but you're sharing on.
Yeah, I share. Can you see my slide?
Yes, I can.
And also
right.
You can see,
Yeah,
okay.
okay.
Okay, yeah. So all of the networks we're interested in, they are spatially embedded, so they need some space to be built. And of course, there is something happening on those networks. You know, there's some dynamics on the system, so they change either the topology over time or there are some movements on the network. And so that's what is interesting for us to model and to understand that. Probably I don't have to spend too much time on these slides because probably you all here more experts than I am. So complex systems depicted as networks. Now, how can we do this and why do we need this? Again, first of all, it allows us to give us a very nice universal mathematical abstraction. So it allows us to deal with a lot of different complex systems in a lot of different settings. Oh, and by the way, maybe I should mention this here. So this is the US power grid when we remove all the spatial features and having a force-directed layout, which is exactly the same as this one here. So that's the US power grid. Yeah, again, we can do a lot of interesting tasks. We can figuring out what nodes might belong together, what features might be there, what behavior might emerge out of these complex systems. And in general, you know, what we're interested in are understanding this kind of collective phenomena. However, and this is where I guess the research we're interested in starts, is like that we have now more and more data on our networks. Now everyone has a phone which records GPS data. When you log in or enter the subway, people know where you enter and exit. So there's a lot of data collecting, flight data. We have all the GPS trajectories of all the airplanes. So there's a lot of data available. And this asks the question, having this kind of data on real world system, is a simple model like a graph still enough to describe what we're actually interested in? Because our data, and when we're looking outside, now it shows that a lot of the systems we're interested in are actually spatially embedded. Now, nodes need space. Edges actually are not only relations to each other, but they have a physical meaning, like a road or a water distribution pipe or any other kind of spatial relation. Then we see networks might be multidimensional. We have different hierarchies within our transportation network. We have highways, we have secondary roads, we have primary roads, we have a transmission grid, we have a distribution grid. So there's natural differentiation between different parts of the network. Of course, and as mentioned before, a lot of the systems we are interested in are dynamic. Now, it's not only the structure, it's also if you're making changes in a substation, for instance, for a power grid, it has influences on other parts of the network, which might be very complex to model. Then another thing is a lot of the part of our network is not known as well. And here I'm again talking about infrastructure systems. So when you bury a pipe, you don't know the state of the pipe. And when it's bursting and you see water coming out, then it's already too late. Now the question is, what's going on while we cannot see, for instance, parts of the infrastructure? And then also relationships might not be as simple as having a one-to-one relationship, but there might be more complex phenomena and things might influence each other in more complex ways. So again, the question is, projecting all of this data into simple graphs, is this a good way to model certain features what we're interested in? And especially in the infrastructure part, we would like to have a little bit more insights using this kind of additional information to make better decisions about our infrastructure systems. And I will give you 3 examples in today's presentation. Let's start with the first one about spatially embedded networks. I will pick out here maybe 3 of the examples. I will talk about spatially embedded networks, higher order networks, and uncertainty quantification in network systems. So talking about spatially embedded networks, one simple question someone can ask is now, how do our cities grow? The question is simple, the answer is very, very complex, and I guess until now not solved actually. However, I guess it's nice to think about this, and maybe, again, you don't have to give an answer, but maybe you can think by yourself. Now, if you have to model the growth of a city, what would be the simplest, well, a simple model you can come up with, which actually describes quite well the spatially embedded networks we observe in cities. So we tried this, and we came up with a multi-layer spatially embedded random network model, and I will guide you through what this actually means and how we use this to make predictions about road networks or infrastructure systems in general and how they are growing. Again, I guess I don't have to mention too much. Maybe I can actually close this one. You can see everything. Again, we're starting with the simple assumption we would have a graph which has vertices and edges. And now the question is, how do we create these vertices that it mimics our real world systems, and how create edges? So the vertex generation is, when we're talking about spatially embedded systems, we have to take into account that each node might be located at a specific point, and it might be located with a higher likelihood in certain regions, while less likely in other regions. So for instance, you can think about each of these nodes as an intersection for a road network. And when you have a denser population, where more people live, you probably need more road networks. Therefore, you probably will also observe more intersections. That's maybe an example. However, another thing which is important with our spatially embedded nodes is that they're not individual by itself. They communicate with other, or you need at least to know where other things might be. And this is where this Markov marked point process comes into the play, where we have that's actually the second part. The first part is that there might be different layers. You might have, this is the Markov marked point process, where we have different layers. We have a XY coordinate, but then also it might be nodes might be fall into highway network category, or maybe in a primary road category. And then the second thing, that's what I want to mention here, is like that nodes interact with each other. So the position of one node depends also on the position of other nodes around those locations. Now, again, you can imagine having a highway intersection. You don't build a next highway intersection a couple of 100 meters next to it. So normally there's a certain distance apart, while other things might tend to cluster more together. And so in order to account for this, again, we added this interaction function, which describes in the first place where it is located in space, given some spatial component. And the second part describes how it is related to other nodes which are already placed on the space, and depending on which layer they are in. So that's the first part. The second part, what we have to think about spatially embedded networks, and that's actually the more interesting part. Let's see if it's working. Is the edge generation. Often this would be a little bit, I guess, not so deeply considered. Often we assume there's a relationship between two nodes. However, in infrastructure systems, the edges are actually the more important things. We're dealing more with railway tracks and roads. And so we have to also think about how they are represented in space. And building roads through mountains is very expensive. It cannot be done. So we also have to take into account that edges and the likelihood of connecting edges depends on the space they are crossing through. And so also here we created a connection model which actually takes this into account, having a kind of spatial field and assigning then a probability based on the way the edge actually will take. So these are the two components we came up with in order to model these kind of spatially embedded networks. Again, having a way to create vertices which are embedded in space, which depending also where the neighbors are located, as well as connecting edges based on a connection model which takes into account that there is certain spatial configurations in between. So let's get.
Before you move on, can you say a little bit more about the interaction functions and the edge generation functions? So how are they related? So
they are not related yet here. So that's one thing. So here what happened is we first generate nodes and then we fill in the edges. So right now, in this particular model, we don't account for, okay, we create, actually we do. There's a special birth and death model where you try different combinations. So it will be taken into account, actually. So it's like what you do is you create a certain node and then you test if this node can stay there or it has to be moved, more or less. That's how this algorithm works.
For the interaction function.
Yeah, for the interaction function, yes. Yeah.
And then the edge generation is something different.
Yes, yeah, so the edge generation has nothing to do. So we place the nodes more or less, and then we ask how likely it is to be connected with each other. Yeah, in this very simple model, yeah. And then again, this connection function depends then on kind of weighted distance between two nodes. Thereby the distance takes into account a kind of spatial field which is underlying our assumption. So it might be the terrain model. No, again, you probably don't want to cross too many mountains if you consider this maybe as a constraint, or we don't want to cross any ocean or anything which hinders this. And so this is taken into account here where we're getting very low weights for very unusual features.
So two vertices may not have an edge, but they would interact. They would have a
yes, yeah, exactly. Yes, yeah. So this, yeah, exactly. This interaction function is independent of the edges. So this is not linked with potential edges. So it's really, maybe go once back. It's really like this. It's like you put an edge there, then the question is, where is the next? And again, we can argue if this makes sense, because normally, I guess you should put an edge and then you should connect this, and we are working on this in another setup. But here in this simple model, it's like we put like a random geometric graph. We put everything on the plate first, and then we try to connect them. Yeah. And this is on the left-hand side. We tested this with Switzerland. So the left-hand side is actually the real-world network, and this is one realization of our random model. Again, it's a probabilistic or stochastic network model. So if you run it again, it probably will look different at the next time. But again, we see there's certain clustering in more populated areas. Yeah, also here we have two layers which are combined. So the blue one is the power grid, and the orange one is the road network, and they are connected to each other. And also there, the position depends on each other, more or less. Yeah, then we tested it if it makes sense, or if certain very simple network measures apply to these spatially embedded random networks. And one of the things we were interested in is speculation by removing either target nodes or edges or randomly. And what you see here, the bold line is our real world network here in red, and the shaded area is our simulated network. Of course, we tested also other approaches. So again, this is this multi-layer network where we then compared the power grid and some network parameters with the underlying ground truth, as well as the road network. And we see in certain areas there's quite some error. In others, it might be better represented. Yeah. So that was one very simple idea of, okay, how can we model spatially embedded networks which represent cities? And we'll come back to this later. So the next thing, what we've done, is a little bit more recent work, is again now the big question was, how can we connect actually different nodes with each other? How can these edges be built in? And the question was, does actually space matter? And so what we tried here is more a data-driven approach. We looked into a graph convolution networks and added spatial information around a certain region to each node. And this spatial information can be anything. So we added, I will show you later in the example, but this can be anything which is related to node, like household income, elevation. What else we added? If it's a city or not, so land use data, and this will be then all connected to a certain node. One nice thing about spatially embedded infrastructure systems is that edges cannot be infinite long. No, we have a certain constraint. We don't want to build a highway which is 100 kilometers long, and you cannot enter or exit in between. So there is a certain limitation on size, which allows us actually to put subgraphs into our learning model so that we don't have to learn all the whole network by itself, but instead we can partition it in smaller pieces and then stitch them later together, because again, edges don't span over the whole area. Yeah, here the thing what we implemented again was more like adding also regional information which are centered around the node to our node features, with the idea that having information about where the node is embedded in might also give us better information about if edges, for instance, are connected or how certain properties relate to each other. And also there we try to regenerate a road network. Again, this is a little bit tilted. It's a California highway network. And here we trained on the Oregon highway network and then tried to create the California highway network. And we haven't given the node location, so we didn't change the node locations, but then all the edges were assigned using the trained model. And here maybe a better overview. So the left-hand side is the original data set. And then here we tried different algorithms, and here our regional spatial graph convolution network actually worked quite well to recreate the highway network in California.
Can you go to slide back?
Yeah.
So the equation on the top, right, x of u of L, you're going over the neighbors. What are you proponent-wise multiplying there? What is the p, what is the x, what is the r?
So here our model has three components. The first one is the position. So we have an x and y component. Then we have a node feature in itself, which is a one-dimensional vector, which is maybe describes the node in itself. And then we have a regional area around each node, which is a matrix, and each pixel represents more like population density, household income, and it combines more or less all the information which the node might be embedded into this model. Yeah.
So is P the lat long?
Yeah, exactly. Yes. Yeah, lat long. Yeah.
And then, all right. Okay, got it. Thank you.
Yeah. So the extension to the other models were like that we added more like these components to it so that they have the regional information. Yeah. Sorry? Yeah.
Could you repeat the question?
Maybe I didn't answer. So what does the feature? Oh, sorry. So the question was, how does this message passing represent the scalar field I showed before? Probably there's no direct relation because this work came later. I guess the scalar field is more like the underlying. So we're cutting a piece away from. So we had here the scalar field. Again, this might be household income. And we assume in this setup that we don't want to model everything because, again, it's a huge amount of data. And often the data is not necessary. So what we are doing is we're cropping out a region around the node. And again, we can discuss about the size of the region. So we tested the different sizes and say, okay, if certain information is a little bit further away from the node, we still take this into account. Now, if you don't take this regional space into account, you might get one value which is attached to this node. But now you're more or less getting a whole matrix which is associated to it. Yeah. So the question was if I computation invariance, permutation invariance. That's a good question. I don't think so.
If you go to that slide where you're summing, I don't think that he is sacrificing permutation invariance, but it's not clear if you have like rotation or reflection or translation.
No, there's just no, there's nothing in there.
But right, because so it doesn't matter the ordering of the name, even though he's including the order. So basically the coordinates are just in a
Exactly. Yeah, we treated it here as a feature, more like as a dedicated feature. Probably it could also be in here, but we wanted to have her as a separate feature. Yeah, maybe that's the best way to describe it. So yeah. Yeah. Yes, that was, again, we applied it to multiple networks, to the highway network, to the power grid network in New Jersey, and it seems quite good results. Yeah, also what we tried, and here I don't have anything published yet on this one, is then adding nodes to it, as again, growing a kind of network and then asking where this might be connected to. Again, it's like you start with a sparse graph and then you add nodes, as I showed you before. And then again, using more or less this data-driven connection function. Now that's what the model before is. Actually, it's like a much more complex connection function than what I used in the first model to ask, okay, are certain things related? And here now we're also trying them out, but again, there's nothing published yet. It's like to have our a loop mechanisms where also the node position will be part of the prediction model. It's like, and if you have a certain amount of nodes, where might be the next node located? Again, even that you have already a connected graph out there, but that's some work in progress. But that is where it's heading. Again, and this is like one small step to getting a better understanding how certain systems might grow in space and time.
You go to slide back.
Yeah.
So when it does make a mistake, did you find that pattern is mistakes?
It's mainly, that's also a good question.
Like maybe it says, oh, put a road on something where like it's very difficult to pass or something in terms of patterns and the false positives or patterns and then false negatives.
Yeah, here the most false negatives are actually in the plane where we don't have so much spatial information. While okay, here maybe one in the mountain, but most of them actually happens in the plane. So here the input features were the elevation map, what you see here, the population density and the household income. So that was the features here. But yeah, we didn't study if we can actually find patterns in what the false negatives are. Maybe it's here as well. Here it's not so well because here it's only the positive collective one, not the false negatives and false positive ones. But that might be a good hint for looking deeper into, okay, what's actually going on there. Thanks. Yeah, let's talk about another work, which is together with my former supervisor, Professor Scholtes, looking into higher order network models. And again, also there we have a very simple question. A lot of people asking, I guess themselves and the researchers, how do people move actually? And as I said before, now we have more access to data than never before. And here, for instance, visualize a couple of GPS trajectories where we know at every point in time and space where the people might be. And again, what is the idea of a higher order network model in the terms of what we are looking at is like past data and past statistics. And yeah, we're getting this kind of past data. Now you can think about this as GPS trajectories where people try to navigate through a network. And then the question is, can we actually model this with simple network approaches? And one, again, approach is in looking into link statistics and depicting it as a network. And there was a great paper in with Nambiot et al., where they have this very nice figure, which highlights it very, very nicely. Is now having this kind of link statistics, we often oversee the history, which might be of importance when we're looking into this kind of higher order data. And then again, going into a higher order step, more or less, where we try to keep track of the history, we can actually better model what's going on. And again, here we can distinguish two data points, the green path and the blue path in this kind of model. And again, the idea is that vertices here in higher order space express actually not a single vertex, but like a walk, so where people are coming from in order to store the memory of yeah, what happened before, and then we can hopefully use this also to predict what comes up later. And edges are more like again an extension of this. Again, we have a causal walk of length k, so it's like adding more to this node feature.
Why are you calling it causal? It's not like I go to this place and it causes me to be in this place, does it?
Yeah.
Sorry, I just like I'm married to philosophers. It's causal, and, you know, it's like proof that this caused that.
Yeah, that's a good philosophical question, if this is causal or not.
Or is it just like it's correlated that when people come to this intersection and they're like, I mean, unless, I don't know, there's a truck that's blocking the way and that causes you to go one versus the other. I don't know. Okay, we'll take that.
It's by construction of the brain graph. So were it not for going to node A, then the higher order node AB in the brain graph would not exist. I think it's like snuck in there. It's not necessarily semantically possible.
Okay, cool. Thank you.
Yeah, and here more like the question is how to apply this to larger data sets, and we collected or got a lot of GPS trajectories all over the world, and most exhaustively in China. Again, because dealing with GPS trajectories is, I guess, sensitive because you can trace back very fast who this trajectory belonged to. So yeah, but there are certain trajectories out, also some in the US, which are open for research. And here we looked into a couple of Chinese cities, and then we looked into PageRank. Again, this is more like a starting point now, what we are looking at, and compared different orders and how they correlate, and if you're getting a better depiction what's going on in terms of this network dynamics if you're looking into a higher order. And we see in this particular case for these transportation networks, we have actually a certain trend in C actually that orders of range of 3 and 4 quite better captures these path statistics than if you would only have first order representation. What we also tried to do, this was done with a smaller network, because again, between the centralities over these large networks is very computationally intense, is to look into a smaller network or Sioux Falls networks, where we try to combine it between or compare the between the centrality, because that's a very frequently used measure in engineering for criticality. However, again, it's only based on the topology and doesn't take into account any dynamics, and a lot of people swear that which node in the high between the centrality is the node we have to fix first. And this is not always true, especially when you have dynamics on the systems. And we could actually show this, that if you're looking at between the centrality and we have the ground truth data, which is the path, and we calculate how often actually a node is traversed, and then comparing it with the first order between the centrality, we're getting much higher deviation from the ground truth between the centrality, or importance measure. Maybe it's not a between the centrality anymore, but importance measure how often a certain intersection will be crossed or edge will be traversed. And then we tried it with only higher order topology. Again, here we don't infer any paths. We only created the higher order network and then ran the same between the centrality and then mapped it back down to the first order road topology. And also there we already see that we're getting a better importance measure, or more accurate importance measure than what we see in the first order case. And then here, last one is where we actually use this path statistics and fitted a higher order model based on the path statistics and use them, this Hans path, to create this higher order space, and then again mapped it back in a first order. Again, here it only shows, I guess, that again, that's also some current work is like that having transportation networks and only relying on topological features on this first order space might be not the best and the optimal way in order to define what is critical on a system, because again, there are dynamics and many other things going on, and blindly saying, okay, between a centrality is the way forward to invest millions of money into certain intersections, certain subway stations might not be a good way forward.
So it's not between centrality, it's the largest eigenvalue of the adjacent region.
What's the story behind Sioux Falls?
Sioux Falls is a smaller network where we can calculate shortest path more easily than in this one. You know, you have to calculate, especially when you go, and that's one drawback with this higher order models. Now that the drawing graphs, now that they grow very fast, and so having here millions of edges in the first order, it would be very, very hard to look into higher order. So that's one challenge we are facing in this direction. So that's why we went to the Sioux Falls, which is a much smaller network where we actually can, even in orders to 4 or 5, still calculate shortest path statistics. Yeah. So the last part of my talk today is a completely different topic, also involves some networks, but again, more from an engineering perspective, and probably he have a good audience to give feedback on my idea on how this might work. Again, maybe the background here is unfortunately very accurate and very timely. This is not, I guess the thing is I stopped at some point adding new pictures. You know, I probably only had to took the news from today. You know, maybe some of you saw the flooding in Spain, which was devastating. This was a flood in Germany, 2021. Also there, over 200 people lost their lives. And the question is, could this have been prevented? And how can this actually happen in the first place? Can we model this? And again, if we can model this, can we do something against that this happens? However, again, it's a very complex problem because a lot of different things fall into this together. So we have to think about the source and know there might be climate change, which can influence the rainfall patterns. The hazard itself is very uncertain, or it changes over space and time. We have objects like this bridge, for instance, but if a bridge fails, it doesn't matter so much because, again, it's only a cheap object compared to the rest. However, again, this bridge might be the only one which leading into a valley, and so all the people within the valley might be cut off from the rest. So we have this kind of network effects. And then what comes on top of this is like we have some societal effects. Now that's often forgotten, but at the end of the day, we as society, we have to pay the consequences. We have to rebuild our infrastructure. We have losses in business interruption, or in the worst case, we lose our beloved ones. So this was the starting question. How can we model these kind of things? And this goes into this system of systems modeling. And this is a more engineering approach right now. So each box, what you see, again, it's not like a classical network of network science, but it's more like a simulation engine, what we created. And each box is a spatial-temporal physical network, physical model, actually a probabilistic model where you have certain inputs and which produces certain outputs, which will be used then on the downstream model. So for instance, you have a rainfall event, which leads to runoff events, so it describes how water goes down the mountain. This leads into flood events, and these flood events can cause severe damages to infrastructures, which needs a restoration, can cause network interferences, and then has to be restored. Traffic might be rerouted. And again, at the end, we're getting direct costs, so we have to spend money to fix infrastructure, but then also have indirect costs because people get stuck in traffic, they cannot go to work. And so it's a very complex model actually to do this. And we created this model. Again, it's spatial-temporal model. Here's a simulation for one 500-year flood event in a small town in Switzerland. And what you see here, actually, in light blue, you see some rain clouds coming from the top, moving towards the south. In purple, you see the traffic flow. You also see here some flood events. In red, damaged infrastructures. And when this happens, the traffic has to be rerouted. You can also, when you look very closely, you see some landslides popping up. So it's a very computational intense model we came up with, but this is what the engineers normally do. However, again, this is only one event, and this is very unlikely to happen. So in order to get reliable results, you have to run this event thousands, millions of times in order to get a kind of distribution of potential events. Again, that's the same hazard event. Now it picked as a probabilistic event where you see the flood zones and how likely certain things are happening. So there's some extreme, again, within the same event, actually. Flood zones, you have a lot of different scenarios where mud flows and landslides can be triggered. On the other side, of course, we also have the impact. And here we have the direct cost, which might be, again, a heat map of where we expect most damages to be happening, as well as the impact on traffic flow. In this particular case, what we see is a much more traffic and traffic chance within the city, while this highway, which is flooded, is blue because, again, no one can use it actually. So coming back to this model here, again, this is more like a depiction how it actually works. And what we have done is we've used very simple physical models for each of the boxes. And if I map this out, it would look something like this. Again, we have here Navier strokes, we have here traffic assignment models, we have a lot of different things out there. So it becomes very complicated very fast. And as I said, running the simulation takes a lot of time. So the question is, can we think about this problem in a different way? And one of my ideas, and again, here, I'm happy for your feedback because there's now some, I guess, work we are starting or thinking about at least, is can we use network representation to represent this very complex physical model without running actually the simulations by itself? So what do I mean with this? Very, very simplified again here is having two inputs, which goes into an equation more or less producing an output. And we can link this with other equations. Again, the idea would be depicting the physical mathematical structure as a network and using this to understand a little bit better this complexity of the system. Again, this is a very simplified version. We can do it a little bit better. Oh, sorry. Actually, before, this is actually the model I showed you before. So exactly using this idea. It's like we went through all the physical modeling stuff and put all the nodes more or less are input parameters. Again, they can be matrices, can be probability distribution, can be anything which comes into our equations and link them together. We have here three different layers more or less. We have the layer within a model, which are the bolded lines. We have interdependencies between different models, which are the dashed line, and then we have a dotted line, which is time dependency. Again, here it's a time aggregated graph. Again, also this we can discuss how this can be produced over time because everything is a temporal problem actually. But here in this particular case, again, it was more like a showcase if it's actually possible. And as I said, we can talk about this one. Another idea would be using expression trees. Now it's like how the computer stores equations without solving them, but in a structured way. Okay, how can we describe this expression in a computer so it can be stored in a simple way? Again, we don't solve it, but it's more like depicting and storing the information in a network structure.
I love networks just as much as the next person, but I'm not quite sure what you're getting by this network representation on the side with all the colors.
Oh, maybe I can, yeah, let's go back.
Because I understood the system of systems,
yeah,
right? And the flow chart you had. And I understand that each box has its own set of equations,
yeah,
blah, 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 right? But I'm not sure, like, what do I get by looking at this network?
Oh, maybe I can, yeah, maybe that's a good point. So I can, so what we have done is, for instance, there is a, let me see, there's a traffic model, which is all the things we need to solve the traffic problem in this example I showed you is based on a couple of equations, again, which we wrote down. And if we unroll this equation and use all the inputs in the equation, we will get these kind of dependencies within an equation. So each color here depicts one of the models we used, and then they're connected because, again, the traffic is needed in order to define the indirect consequences and the direct consequences, which are over there, more or less. So the idea is, again, here also it's only describing all of the equations we have. Again, each of the stuff we more or less divided it and said, okay, this is the flow more or less, which depends on the raster cell and the time point. And so this would be Q, which depending on a variable R and a variable T, more or less. And again, this will come into this equation and other values coming in. Again, it's more like a depiction of physical model of the network. That's
so if you go forward to the next slide,
yeah,
the slide with the network. So like here, can I say like 11 is really important? So for node 11, which is rainfall, so I have to get that really right. Or maybe no, 12 doesn't matter as much.
Yeah,
and
so
I
that
won't
would be
spend as
the
much
that would be the idea.
money
Yes, yeah,
on
yeah.
12. All right.
Exactly.
That's
Yeah,
fine.
so yeah, that would be the idea. So this is like the model. The idea would be, again, let's think about how certain things might depend on each other. This is more like what the paper we wrote, more or less, if you use all the physical equations and put them in relationship to each other. So here, again, it's more, instead of writing the equation out, we making a network out of it, more or less. That's the idea. And again, it's in an early stage, and we can debate on this. So one thing we tried is, again, community detection and seeing how certain things might belong to each other, and then do they actually belong to each other. We see here, again, we have the traffic model in green, and again, running a community detection algorithm, simple one. We see already here, there is already some yellowish, which depicts this nice, but also here it says that because the algorithm would also see parts of the indirect consequences, which is over there, part of the traffic model, because they're very intertwined, so they're very, very strongly related. Because one big question always with engineers is, what model do you use and how accurate these models are? Because there are hundreds of models out to solve traffic assignments. There are hundreds of models out for flood. And then the question is always finding the right models and piecing them together. And yeah, so that might be one idea to see, okay, certain things, how they belong to each other, and would we expect that they should be together, or do we see something that certain things might appear in other parts? So what we see, for instance, over here, this is the bridge damage model in the middle here, the damage model, the blue one, and this has certain parts which reaching out to other branches, which probably are closer to the bridge damage model than to the direct consequences, for instance. Then this is probably what you said before, is like we have certain parameters what engineers can actually change. And we call it here now source and then the sync nodes, which are more like the output you want to observe, like, for instance, risk or other things. So here the idea is seeing actually, and this is, we'll show you in the next slide, is like, okay, if we have in kind of a random walker or some diffusion process on this, could we actually figuring out what might be important for certain parameters so that we understand better the models. And here, for instance, we start with a diffusion process. This is, again, the damage model in the middle. And we want to know when we're changing the bridge pier width, again, this is the column, the middle of the bridge, how does this affect the overall system? And here we run a couple of these kind of simulations where we see, for instance, here the bridge pier width has a very strong influence in the direct and the damage section, which we expect. And we see also where the outputs might be. The precipitation, which was our input variable, has other stronger influences. And then here we have the time. Again, here the problem was that we everything aggregated into a static graph. Again, actually, it's a temporal graph and certain things changing over time. And here the time influences everything more or less. That's why we don't see so many red points. And then it aggregates very strongly with the risk. So this is the cost section, the risk we observe, this node here.
So the function nodes have double rings and the inputs have single?
No, here the double rings is like an equation. It's like a couple of things coming together, merged together in some way. In this particular case, yeah, exactly. Yeah, but not all variables can be changed. So here there are certain, again, source nodes which don't have any in edges, only out edges, and certain sync nodes which only have in and no out edges. And these are the things that normally can be changed or can be modified. And then the question is, how does it propagate through the system? So that was the idea, more or less. And again, this is more the network science part. Now let's go more to the engineering part. So how we engineers define a system failure is actually a probability distribution, a very high dimensional probability distribution, where we have random variables which describe the state of our system. And in a certain case, we fall into a failure domain, and this is a state we don't want to have, more or less. And what we're doing is we define a limit state function, which is G, and this limit state function describes the behavior we don't want. So that, for instance, collapsing of a bridge is something we don't want, so this is described with this limit state function. Again, this can be decided based on the problem you want to solve. And then we have here a system model. This, again, can either be a finite element model, it can be a network model, it can be any model, which, again, is a probabilistic model depending on our random variables. And I guess the part what we have to do is actually we have to solve this integral, which is very difficult to do or impossible in certain cases. But again, there's certain techniques to simplify this in order to get an estimation about the probability of failure. And so the idea would be the next step also link this kind of modeling approach, more network approach, and see can we combine this kind of engineering approach with a network approach. Because again, here this is I think work we're doing on a regular basis in structural engineering, like again finding out what might be important there by modifying a little bit about our inputs. Here again, one trick to solve this is like putting into a isoprobabilistic space where everything is Gaussian, more or less approximated with Gaussian. Again, strong assumptions, but it makes it feasible to calculate a design point, so the most likely point of failure in a very high probabilistic space. And then again, we can play a little bit around and see what might be the inputs or the impacts of certain variables on our overall system. And then, of course, we can do also sensitivity analysis, having model parameters, be it some fixed parameters or being parameters of our distribution function. And then we can figure out what is actually the influence of certain parameters. How sensitive is our model against changes to certain model parameters? Again, this is now work we're currently working on, is like to combine this network approach with a structural reliability approach, and looking then more into this higher probability distributions and how certain things might link to each other. And again, the idea would be that the system model is, instead of a finite element model or an engineering model, then more like a network model to understand a little bit better what's going on there.
5 minutes.
Okay, perfect. Because I'm already at the epilogue, so already at the end. Also there, I want actually to use this to probably getting your feedback on something of interest for me. And maybe we can use this as a starting point of discussion, and also for dinner or later on to discuss about this. So again, the problem is coming back to the first part, like spatially embedded networks. And again, this is a network in the UK we looked at. And one thing, again, in order to use network science now to understand those things, is we depict and say, okay, intersections might be nodes and edges the roads might be edges. And already here we see we're making an approximation. No, we have very complex shapes as our edges, and then we only approximate this as a line often. So one thing which is missing is like, okay, really how these edges are embedded in space. The second, more interesting part I came across, and maybe someone of you has the answer here, is that our infrastructure systems are very, very large. And often what we're doing, and when you look in any engineering paper, is people taking a smaller subset. I showed you before the set of a city in China or parts of Switzerland. So what we're doing is we're having a huge graph, and then we sample from the graph. We're setting a boundary around it, a spatial boundary. And then the question is, what is now the right depiction of the network? Do we have any boundary effects actually in spatially embedded networks? I couldn't find any good solution yet. I know in spatial statistics, they dealt a lot with boundary problems for point processors. But for spatially embedded networks, I couldn't find any satisfying answer. Because again, here, assuming that we cut away all the edges which are outside of our boundary, what happened with changing actually the underlying structure of our network? And then the question is, if you analyze this system, do you have some biases? Do something change? What you cannot really represent, especially when you're dealing with graph properties. And if you're dealing something very local, maybe it doesn't matter because you can draw a large boundary around. But if you're dealing with global properties of graphs, then of course, everything outside also might matter. And the second picture I pointed to you here is, again, this might be another way to depict this boundary problem. We cut everything off which is along the boundary. Also here, we introduce features and artifacts that does not exist in the original network. Here we have a disconnected network where the length of the edge is not even in reality there. So yeah, that's a problem I came across. Most of the engineering literature you look at, they assume kind of network and never ask the question, does this actually change anything in our analysis if we're taking this boundary? So if anyone has an answer to this question, I would be more than happy to get this. Otherwise, yeah, we're working right now on a grant proposal. So if anyone wants to join as well, that might be a good opportunity. And before I close, if you know someone who might be interested in studying infrastructure systems, I'm looking for motivated PhD students as well as postdocs in the terms of uncertainty quantification of network systems, as well as spatially embedded networks. So if you know anyone, please forward this message to them. So I'll be more than happy. With this, thank you very much. Thanks for your time.